Having learned the basic concepts about forces, we are now ready to explore what is meant by balanced forces and how that relates to Newton's first law of motion. You must have realized that when you are in a moving vehicle and if it stops suddenly, you will jerk forward. Similarly, if you are in a stationary vehicle and when the driver starts driving, you will jerk backwards. Why is this so? What's the physics behind this? This is what we are going to learn in this course of dynamics. In dynamics, we learn about the forces acting on objects as it is stationary or in motion. The reason why we jerk forward when the bus stops suddenly can be explained by the first law of motion instituted by Sir Isaac Newton. Newton's first law of motion states that every object will continue in a state of rest or uniform motion in a straight line unless a resultant force acts on it to change its state. When the bus is moving, we are moving. When the driver jams his brakes, it is a force that stops us, but at the initial stage, we are continuing our uniform motion in a straight line as described by Newton's first law of motion. Hence, we jerk forward. Likewise, when the bus is stationary, we are in the state of rest. When the bus driver starts the engine and moves forward, there is a force acting on us while we are still in the state of rest. Hence, we jerk backwards. Let's study in further detail Newton's first law of motion. First, let's look at objects at rest. If you have a ball resting on the ground, we know that the ball will remain at rest until someone exerts a force to kick it and get it moving. So this is a clear and simple example of Newton's first law of motion about a force being applied to an object at rest. However, in Newton's first law of motion, the word resultant force is used instead of simply the word force. So let's find out what is a resultant force. Suppose two persons are pulling an object. If one exerts a force of 500 Newton and the man in red exerts a force of 600 Newton, then there will be a resultant force of 100 Newton towards the right. A force is a vector, so if you set one direction to be positive, the other direction will be negative. When you add up the forces, you will get the resultant force with a sign indicating the direction of the force. In such a situation, we describe the forces as unbalanced. So when forces are not balanced, there is a resultant force, and objects will move towards the direction of the resultant force. In fact, this brings us to Newton's second law of motion, but we will study that in the next lesson. For now, we have more to learn on Newton's first law of motion. Now that we have learned what is meant by resultant force, let's examine what if each of them exerts an equal force of 500 Newton. In such a situation, the forces will have cancelled each other, and the resultant force is therefore zero. So nothing moves. We say the object is in equilibrium, and the forces are described as balanced forces. Next, let's look at applications of Newton's first law of motion for objects in motion. We shall use the example of falling objects. If you recall, we have learned in the course of kinematic that objects falling in the presence of air experience both a force of gravity, which is the weight of the object, pulling it downwards, and an upward frictional force, that is the air resistance, that opposes the downward motion. So in this case, when the ball falls off the cliff, it falls with increasing speed because of the force of gravity pulling it downwards, but the increase in speed is at a decreasing rate because the upward air resistance increases when the falling speed increases. We have also learned that the upward air resistance continues to increase until it is equal to the weight of the object. At this stage, the object will fall at constant speed, which we term as its terminal velocity. When the downward force of gravity equals the upward air resistance, we say the two forces are balanced or cancels each other, and the resultant force is zero. So when the ball is traveling at terminal velocity, that is, it continues in its downward straight line motion at uniform velocity, it is another application of Newton's first law of motion. Take note that when the ball is falling at terminal velocity, which is constant velocity, and which also means that the acceleration is zero, it does not mean that there are no forces acting on the ball, even though the acceleration is zero. The force of gravity is always acting on the ball, and the air resistance is still acting on it as long as it is falling. It is just a case of balanced forces. Similarly, when you have a box resting on the table, not moving, nor falling, it does not mean there are no forces acting on the box. In fact, there is a force of gravity pulling it downwards, and there is a contact force acted by the table supporting the box, preventing it from falling. These two forces are balanced, and so the box is in equilibrium, not moving. We will cover this in more detail in later lessons. To conclude, when an object is acted upon by balanced forces, the object is in equilibrium. It is a case where there is no resultant force, and hence a situation where Newton's first law of motion applies. If the object is at rest, it will remain at rest. If the object is in motion, it will remain in motion at constant velocity. So the acceleration is zero when forces are balanced.